Okay, in this video, we're going to start working our way into the topic of integration, and we're going to be looking more along the lines of what definite integration is, and what we're going to see as we progress forward through this unit in a few videos is that definite integration allows us to find the value of the area up underneath the curve, and we're going to begin here with an exploration problem where we are trying to determine the amount of water that's in the tank after a certain amount of time. Now, what we have is the tank's being filled with water. Now, the pump is old, and as it runs more, it starts slowing down. I see that here in the rate column. It's pumping 42 gallons per minute to begin with, and then it decreases all the way down to 10 gallons per minute by the end. And we're told that the tank is initially empty. So how much water is going to be in the tank after 90 minutes? Well, to estimate what this is going to be, the amount of water that's in the tank after 90 minutes is going to equal basically how much we pumped in, which would be the rate per or time interval. So the rate times however much the time interval elapses. Now the issue is we don't have a constant rate that is going on. It's changing, and it's the pump's slowing down as we go forward. So we're going to use an estimation process. Now, what we're going to do is we need to take our time intervals, where we go from 0 to 10 and 10 to 20, and we are going to create subintervals here from 0 to 90 minutes. So I'm going to go ahead and write those out. Okay, so we have the time intervals written out here. Now, we're just using the numbers that are in the table. So each interval elapses is going to be 10 seconds. So we got an interval from 0 to 10, 10 to 20, 20 to 30, and so on. And so when we're going to try to estimate the amount of time, or excuse me, the amount of water in the tank, the amount of water is going to equal, well, I need to estimate how much water was pumped inside of each interval of 10 minutes. And so what we need to do is we need to pick a value to use for our rate. And so, for instance, let's look at this first interval that goes from 0 to 10. And so what we have to do is we have to pick out the rate that we want to use for each little time interval. And just for the simple case of what's going on, what I'm going to do is I'm going to use whatever the left time value is for the time intervals that we made. I'm going to use the associated rates that go along with those. And so I have those written here up underneath the subintervals. And so we're going to approximate the amount of water that's in the tank by taking the rate and multiplying it to the elapsed time. So for instance, the amount of water pumped into the first in the first 10 minutes would be 42 times 10. The second 10 minutes would be 40 times 10, and then keep going, so forth. And so after we do that, so we pick the left endpoints of all of these intervals to use for our heights, or not for our heights, for our rates, and then we multiply that to the elapsed time as I have written out there, and we wind up getting a sum for this amount that's going to be approximately 2,890 gallons. Now let's think about how we got gallons as our units. We started, so we had the amount was equal to rate times time. Well, our rate in terms of units was gallons per minute. And if I multiplied by the units for our time, which is minutes, if I multiply gallons per minute by a minute, the minute part would cancel out and just leave me with gallons in terms of our unit analysis. Okay, so next problem here is we want to find the area up underneath the curve from x is equal to 0 to x is equal to 12. Now, if we're fortunate to have a graph like this, we could use geometry rules where we're going to come through and we're going to find the individual areas between the curve and the x-axis. We're going to add them all together. So for instance, I have a square that's right here first, so that area would be 4, and then we have a rectangle right here that we're going to try to find the area of, and we would have 4 times 2, which would be 8. And then we reach this next part here, which is initially not an easy shape to work with. However, if we break this thing apart into individual pieces, we have a triangle here on the left-hand side. All right, and then we have a rectangle, and then we have another triangle. So the area of the triangle that's up here, 1/2 base times height, is going to give me 2 for an area. And then we have our rectangle down here, which what we have is we have 2 for a width and a height of 4, so we get 8. Now we're here for this next rectangle, 1/2 base times height. We have a base of 2, a height of 6, so 1/2 times 2 times 6, I get an area of 6. And then now we're here on this semicircle, which the area of that semicircle would be pi r squared divided by 2. Well, r is going to be 2, so pi r squared would be 4 pi, but I got to half that number, and so this area would simply be 2 pi. And so the area between the curve and the x-axis would be the sum of all of those individual areas, which we would get 28 plus 2 pi as the area between the curve and the x-axis. All right, which takes us to our next part. And so we're not always given situations where we were going to try to find the area up underneath the curve and we can just apply geometry formulas. Kind of like in that first example that we looked at with the table, where that pump was constantly declining, but it wasn't a constant rate. It was different over each subinterval. We didn't really have an equation to work with. What we can do is we can approximate the area up underneath the curve. So if I look over here on the right-hand side, like if I have a curve like this, and I wanted to approximate what all this area is, we can apply some geometry formulas for the approximation. And we can use a rectangular approximation, which abbreviated would be RAM, to determine what this sum is. Now, the type of rectangle we draw will depend on the kind of method it is we're going to use. For instance, I could use right rectangles, left side rectangles, or in fact, I can even use the midpoint. And we'll talk about how it is we're going to do that with an example of each one right here below. So we have 4 rectangles that we want to use to approximate the area up underneath the curve of this quadratic function in between 1 and 3. First thing that you want to do is you got to find the width of your rectangle. So basically it's going to be my change in x. My change in x in this case would be 3 minus 1 over the number of rectangles that I want to use, and that's going to give me 0.5. So each rectangle I'm going to draw is going to have a width of a half. And so we'll start with our left endpoint. So we're only going from 1 to 3. This is the region. We want to approximate that area right there. Well, if every rectangle that I draw is going to have a width of a half, so left endpoint, LRAM, means that I'm going to use the left side of my rectangle is going to come in contact with the function, and then I'll come over to the end of that interval and pull back down. So there's one rectangle where the left endpoint is the one that makes contact with the curve. My second rectangle would start at that same endpoint, come up to where it contacts the curve. So I would come up to where it contacts the curve, and I would go over my half unit, and I would come back down. And then I would continue this on until I have my 4 rectangles. So my third rectangle would come up. The left endpoint of that rectangle is on the curve. And then I would go over my width of a half a unit. And then I would come back down. And then lastly, we get to our 4th rectangle. We'd come up. Its endpoint would lie on the curve. We'd come over. And we'd come back down. And so we're approximating the area up underneath the curve by using these rectangles that have their left endpoints as the height of the curve. And so let's go find that area. So basically what we're going to do here is, as you see it graphically, if we're finding this area, is we're going to take each of those rectangles is going to have a width and a height that I'm going to use to determine the individual area. So the width of the first rectangle is 0.5. The height of that rectangle is the function's value at 1. So base times height is going to give me that area. Then I would go plus, get to my second rectangle, which would be 0.5 times f of, for its height was the function's value at 1.5. And then we continue on and go, okay, third rectangle, width times height, so 0.5 times 2, plus 0.5 times 2.5, f of 2.5. And that's how we would get our values. And so we continue on. We go get those function values. Now you can try to estimate them off the graph and use those values if we're not in between and we're actually on one of our grid marks. But the most accurate way to get these values here is to actually put these numbers into the equation of the function that we were given to work with. And we do that and we get a sum of 3.75 for this left approximation method. The next approximation method I want to do is going to be RAM, which would be the right rectangular approximation method. And so graphically, let's come over here to, we have the same curve, all right, and we're looking inside of the same interval. So my interval, we're going from 1 to 3 still, all right, so I'm going from 1 to 3 to approximate that area up underneath the curve, but a right rectangular approximation method. Now we're still using those same rectangles that have a width of a half, which means that I start with the right side of my rectangle and I go up until I intersect the curve, and then I'm going to come back over to the left. All right, so there's my first rectangle that I draw. So it goes from 1 to 1.5. The second rectangle that I draw would go from 1.5 to 2 because it has that width of a half. I come up until I intersect the curve, and then I work my way back to the left, and I'd come back down to the x-axis. My third rectangle would go from 2.5, come all the way up here till I get to the curve, and then I'd come over here to the left, and then I would come down. And so there's rectangle number 3. And rectangle number 4 is going to have a height that's going to be determined by the function's value on the right side of the interval, which in this case is at 3. I come over half a unit and I come back down. So this method, using the right rectangular approximation method, we are approximating the area up underneath the curve by using these right side rectangles here. So the sum of the 4 individual areas of these 4 rectangles would be our approximation. And so we're going to write out an equation that represents the sum of those areas. Okay, so approximating this area of the 4 rectangles we have here, we would find it would be base times height for each of the rectangles. Well, the base of each of those rectangles is 0.5. The height of the rectangle is determined by the function's value at that particular place using function notation. That'd be f of whatever the right endpoint is for each of those intervals. Now we would go get those y values for the functions, so that way we can have our heights. The most accurate way to get those y values is by plugging these numbers into our original equation instead of just estimating them off the graph here. And in using that approximation method, and we get their heights, and we find the area of all 4 rectangles, we get a sum for this area up underneath the curve to be about 5.75. Our last rectangular approximation method is going to be MRAM, which is an acronym for midpoint rectangular approximation method. And so we go to the graph of the same function. We'll see what midpoint rectangles look like. Now we're still trying to estimate the same interval from 1 to 3. Now the height of our rectangle here, see, we're looking at our span. Each rectangle is only half a unit, so I'd go from 0 to a half is going to be the width of my base. The difference is that the height of this rectangle is determined by the middle value of that interval. So that height, the point that's going to share the value with the function, is going to be in the middle of the interval. So I'll have a little bit of the rectangle, in this case, above and below my curve at the same time. So there's my first rectangle. My second rectangle would span the interval from a half to 2. The height is going to be determined by the middle x value of that interval, and then we're going to complete our rectangle that we draw. And then we'd go from 2 to 2.5, and so the height's going to be based on the middle x value, hence the name midpoint. And so we'll draw that third rectangle, and then our fourth rectangle would go from 2.5 to 3. So halfway in between there, we would determine our height for our approximation, and then we would continue drawing our rectangles. So this time we're going to approximate the area beneath the curve by adding together the individual areas of these four rectangles whose height is determined by the middle x value of the sub-intervals. And so let's write an expression that represents this area. And so our expression here, the x values that we use were in the middles of all of our intervals for the height. So halfway in between 1.5 is going to be 1.25. Halfway in between 1.5 and 2 is 1.75. Halfway between 2 and 2.5 is 2.25. And halfway between 2.5 and 3 is 2.75. And so now we would go get their y values. Remember, you can estimate the y values by looking at the graph, but the most accurate way to get the true y value is going to be to plug those x's back into the equation. Okay, so we plug those x values in and we get these corresponding y values here. So we take and find the area of each rectangle, which in this case width times height or base times height. Add them all together and we get an approximation of 4.25. Notice how all these approximations have different values. Now graphically we can look at them and compare. Is our first rectangular approximation method was an under approximation. We had all this empty space. And our second approximation that we used, the right endpoint, we had a lot of space that was above where the function actually was. We ended up over approximating, and the midpoint kind of split the difference and was somewhere in the middle of those two approximation methods. Okay. Well, here we go. We got another example here. This time we're going to go back to using a table like we did at the very beginning. So the table shows the velocity of a model train engine moving along a track for the 10 seconds. I want to use two approximation methods that I have here over the given intervals, and we want to estimate the distance traveled by the engine in the first 9 seconds. Well, look at what you're given. You're given velocity and time. So remember that distance is equal to rate times time, or velocity times time. So if we use the time interval times whatever the velocity is, we can estimate the distance traveled. Well, our first problem here, we want to use left rectangular approximation method using 3 subintervals in the first 9 seconds. So we'll start by finding the width of each subinterval, which is my change in x. My change in x, or in this case it'd actually be change in t, would be the overall span. So first 9 seconds would go 9 minus 0 over the number of subintervals we wanted. And so each subinterval would be of width 3 seconds. And so we would write out our subintervals representing these time spans. And so we write out these 3 subintervals, and we go from 0 to 3, 3 to 6, and 6 to 9. Now we want to use LRAM, so left endpoint rectangular approximation method. So we're going to use the left numbers of each subintervals to determine the height of these rectangles to find the areas. So if I write this out, it would be the width of the subinterval, which is 3, times the function's value at that particular point. So my first area would be determined by 3 times f of 0. Then I would go plus the width of my second interval times the function's value at that left endpoint. And then plus, I do it one more time, the function's width of the subinterval, or the width of the subinterval times the function's value at the particular point. And we're using all left points. Now we would go get the y values from the table, and then we would evaluate. And so the y values would be 0, 10, and 11 respectively. We find those areas, we add them together, and we wind up getting 63. And then we need to attach units to this. We were in centimeters per second, and then our time was in seconds. We multiply those together to approximate our distance, and we get 63 centimeters as the approximation of the distance traveled. All right, now we want to do midpoint rectangular approximation using 5 subintervals to estimate the distance traveled in the first 10 seconds. Well, we need to find the width of our subinterval. I'm going to call it change in x. That would be, so we'd go from 0 to 10, and we want to break that up into 5 equal intervals here. And so we would get intervals of 2 units. So we would write those starting from 0 going all the way to 10 that has widths of 2 seconds. All right, so I write out those subintervals. Now we're using midpoint rectangular approximation. So within those subintervals, the heights that we're going to use for the rectangles are going to be in the middle of each of these. So I need to find the middle value of each subinterval to determine my height, which would be 1, 3, 5, 7, and 9. And so our area for the individual rectangles would be the width of the interval times the function's value at that midpoint. So the first one would be 2 times f of 1. The second one, we have a width of 2, and it would be times the function's value at 3, plus we have a width of 2 times f of 5, plus the width of 2 times f of 7, plus a width of 2 times f of 9. And we would go get those values from our table and plug in. And so we plug in and we get these values out of our table. Now the function value really is the velocity that we're talking about here. And we add all those together and we get an approximation of 94 centimeters using this approximation method. All right, another way to use geometry to approximate is to use trapezoids. And trapezoids are going to be more accurate than our rectangular approximations in most instances, just because of the geometry we have behind finding the trapezoid. Now the trapezoids we're going to use are all going to look like this over here on the right, where the height of the trapezoid, this is a trapezoid where we have a right angle here formed between the two bases. That's how we find our height, which also represents the width of a subinterval. Base 1 and base 2 are the two parallel legs. I'm not worried about the slanted piece. So the area of a trapezoid, remember, is h over 2 times the sum of the two bases. And then we would draw it out, and then we would add the areas together. That would be our first method. And so here we have, looking at this first problem, we want to use 4 trapezoids to approximate the area up underneath this parabola again from 1 to 3. All right, well, before I can do that, I need to get how wide is each trapezoid going to be. Well, we're going to go from 1 to 3, so my width would be 3 minus 1 over the number of trapezoids I want. So my width is 0.5, again, for each subinterval. So that's going to be my change in x. So we're going to go in here into our graph, and I'll zoom way in, and we want to draw a trapezoid. So each trapezoid has a width of a half unit. So my first trapezoid here, what I do to draw it is I draw 2 vertical legs that touch the curve, and then I connect them with a straight line. So there's one trapezoid, and then I would draw my second trapezoid, which would go from a half to 2. I draw the 2 lines up. The left side line's already drawn. Then I would go to my right side, up to the curve, and then I would connect the 2 with a straight line. And then my third interval would go from 2 to 2.5. I draw a line all the way up to the curve. And then I close in my trapezoid by connecting the 2 endpoints. And then my fourth subinterval will go from 2.5 to 3. I draw a line on the right side of this interval, and then I would connect the 2 endpoints together with a straight line, and that would be that fourth trapezoid. Now the area that we're using to approximate is the sum of the area of these 4 trapezoids. Notice how close and how tight of a fit it is in this particular example. Much better fit than our rectangles. So what we want to do is we want to find the individual the individual height of each of these trapezoids that we have, and we're going to write it out and add them together. All right, so we're basically looking at these individual subintervals. Now what I'm going to do is, for me it makes it a little easier, but you also have your picture here. So the area of my first trapezoid, which is working on that very first subinterval here on the left, the area is the h, which is the width. The width of that subinterval is a half divided by 2 times the sum of the bases. Well, the bases of the function are the y values at the 2 endpoints. So f of 1 plus f of 1.5. And then I'm going to write that out for all of these intervals, and then we're going to fill it in, and we're going to find the area. All right, so we fill this thing out. We continue writing out where we're getting our y values from, and then we get our y values of our function at each of those intervals there. And then we get a grand total for the sum of the areas of those 4 trapezoids to be 4.75. Remember where those y values are coming from. They're coming from the y values of the endpoints of each of these intervals. Now, there is a second method to doing trapezoid approximation. Is if you notice, as you're doing this problem, we ended up using some values multiple times. So for instance, we had the same height because we had subintervals of equal width. And so I had 0.5 divided by 2. That's the h over 2 part. And then if I were to factor this out, oh, let me do a different color. If I would factor off that common factor that multiplies to all of those, and look at what I have left. Well, what I have left is I would have f of 1, and then plus, and then the next thing that you'll notice is you're going to have some of these that repeat. F of 1.5 shows up twice. F of 2 shows up twice. F of 2.5 is going to show up twice. And I had an error in this interval, but I used the correct y values, but my error here, I had to change that. That should have been f of 2.5 to 3, but now that's fixed. But that 2.5 shows up twice as well. So I could just say double those individual y values that appear twice. So 2 times f of 1.5 plus 2 times f of 2 plus 2 times f of 2.5 and then plus f of 3. And we would get the same answer. Now, we can generalize that process. Now, this process, again, only works, this second method only works if all subintervals are of equal width. And we could save ourselves the trouble of finding the individual areas. However, and we would get the same answer of 4.5. However, the most common times you're using this is when you're evaluating and approximating either graphically or from a table, and it could just be easier to use method 1. And so both of these methods, again, would yield 4.75 as an answer.